こんにちは。プリファーネットワークスの高木と言います。今日のトークなんですけど、ちょっとオースティン、この7月にSciPyオースティンで同じトークをすることになっているので、ちょっと今日も英語でさせていただければと思います。I have this talk in English because I will have the same talk in SciPy Austin this July, so I'd like to practice for that. Then, okay, let's begin. Today I introduce CuPy. CuPy is a NumPy-compatible library for high-performance computing with GPU. This is today's goal. The intended audiences are those who involved in generally scientific computing, such as researchers, data scientists, software engineers, and especially ones already use NumPy in their works. And today's goal is please try CuPy after this talk. Then we hope CuPy will be applicable to your works. Then note that I don't talk about CuPy's design and its technical details here today. So if some of you have interest in such technical topics, please let me know, and I may have such technical talk on another chance. Then please let me introduce our organization briefly. Prefer Networks is a new startup in Japan. It was founded at March 2014, and it has more than 120 engineers and researchers. More than $100 million investment from Toyota Motors for autonomous driving, and it got second place in the Google AI Open Images the last year. And with new ML2 private supercomputer, it will provide totally around 200 petaflops computing resources. And our business domains are deep learning research and its industrial applications as automotive, manufacturing, and healthcare. Then CuPy's talk about CuPy. First, CuPy is an open source Python library, and it has NumPy-compatible API and brings high performance in n-dimensional array computation with Nvidia GPUs or CUDA architecture. These are the key benefits of CuPy. Drop-in replacement with NumPy, high performance, and open source, and actively developed and maintained. I will explain these points one by one. First, drop-in replacement with NumPy. CuPy is designed to be highly compatible with NumPy, so it enables you drop-in replacement on your code. This is a snippet written in NumPy, importing NumPy, and creating two n-dimensional arrays filled with random numbers, and computing dot production of the two arrays. Then how does it look like with CuPy? Here it is completely the same except this module name. Importing CuPy instead of NumPy and creating two random arrays, then computing dot production. Since modules are the first-class objects in Python, you can share the same code between NumPy and CuPy. Here is an example. And conventionally, we assign NumPy or CuPy module to a variable named xp, then use the xp module as usual NumPy code. Look like this. And please see the more practical use cases on CuPy's sample codes. Then why did we start developing CuPy? CuPy was originally a part of Chainer. Chainer is our neural network framework, and the purpose is to provide both CPU and GPU support with lesser effort. And the left is a screenshot of the initial CuPy release. And at that time, CuPy was in China's repository. And the right is the original author of CuPy, Okuta-san. And he is now CTO of Proof Networks. And CuPy widely covers the features of NumPy, and it will be, we suppose, enough in the most cases. CuPy supports these fundamental data types for each data size, and all basic indexing, and most of the advanced indexing, including the Boolean array masking. Most of the array creation routines are empty, ones like and diagonal. And most of the array manipulation routines as reshape, roll axis, concatenate. And it, of course, supports all operators with broadcasting, and most of the universal functions for element-wise mathematical operations and linear algebraic functions as dot, matrix multiplication, Koretsky decomposition, and singular value decomposition. It also provides reduction along axes, sorting operations, and sparse matrix. Additionally, CuPy supports some of SciPy libraries features, such as Fourier transform, linear algebra in CuPyX, SciPy ring-arg module, and n-dimensional image processing, sparse matrix, this CuPyX SciPy sparse module, and special functions as gamma function or zeta function in CuPyX SciPy special module. And there are remaining features unimplemented, so please contribute CuPy to make it more matured. The second point of CuPy's benefits, high performance. CuPy brings high performance and dimensional array computation for large data size with Nvidia GPUs. Here is a simple benchmark of matrix addition, creating two arrays, n-dimensional arrays, then adding the two arrays. Then please see the blue line for CuPy and the yellow line for NumPy on the chart. And the vertical axis is processing time, so lesser is better. And with a size of around 10,000, CuPy is more than 10 times faster than that of NumPy. And another benchmark of dot productions, creating two square matrices, then computing their dot production. Similarly, with the size of several hundreds, CuPy is more than 10 times faster than NumPy. Then roughly saying, CuPy is faster than NumPy with the size of data more than that of the CPU's L1 cache, then around 100 kilobytes or so. And to make full use of the GPU architecture, CuPy uses CUDA's related libraries provided by Nvidia. For example, cuBLAS and cuSolver for linear algebra, cuSparse for sparse matrix, then cuRand for random number generation, and Trust for sorting operations. So you can get easy access to such libraries from Python. The next, third point of CuPy's benefits. CuPy is an open source software, and you can access its entire source code on GitHub. CuPy has more than 2,900 GitHub shares and more than 150 contributors. And it is provided under MIT license, so it is also legally easy to use. You can send feature requests as well as pull requests. So, we are actively merging such contributions. Other than China, several projects use CuPy. One is Pomegranate for probabilistic and graphical modeling, and another is Spacey for natural language processing. Then I also heard that a project used CuPy for Fourier transform on GPU. And we'll be happy if you let us know your project using CuPy. Next, the fourth point of CuPy's benefits. CuPy is so actively developed and maintained that it has more than 13,000 commits and monthly continuous releases. The left is a table of recent releases. And the latest release was at 4th of April, including stable version 5.4.0. and the development version 6.0.0 release candidate 1. And CuPy version 6, the next major version up, is scheduled to release officially at the beginning of the May after the Golden Week holidays. And here are the updates in the latest stable release version 5.4.0. Then the latest CUDA 10.1 and cuDNN 7.5 are now supported. And the CuPy starts to compile kernel codes for compute capability 7.5 for Turing GPUs. And it contains several enhancements and bug fixes. And please check it on CuPy's release note. And this is CuPy and its benefits. Then next, I explain how to get started with CuPy. If you have access to an Nvidia GPU installed computer, you can install a pre-built binary of CuPy just by pip command. First, download and install CUDA toolkit from the NVIDIA's official website. Then type pip install CuPy-CUDA 101 on your terminal emulator. And this 101 stands for CUDA toolkit 10.1. So if you use the older CUDA toolkit, for example 9.2, please modify the package name as CuPy-CUDA 9.2. Then of course, you can install CuPy from its source code when the pre-built binary does not meet your requirement. And please see the detail on the official installation guide. Yeah, and even if you have no access to Nvidia GPU, you can still try CuPy on Google Collaboratory. The left is the screenshot of Google Collaboratory on which NumPy and CuPy runs. And one point, please do not forget enabling GPU on Google Collaboratory. And from its menu, select runtime, then change runtime type, and choose GPU for hardware architecture. We also provide official tutorial and sample codes for CuPy. The left is the capture of CuPy's tutorial, and the right, I list some of CuPy's sample codes. Conjugate gradient method and financial pricing such as Black-Scholes equation and Monte Carlo simulation. Then Gaussian mixture model and k-means clustering. CuPy contains such sample codes. I show briefly the k-means clustering sample code. K-means clustering is algorithm to partition n observations into k clusters, in which each observation belongs to the cluster with the nearest mean. And this is the implementation of k-means fitting function that runs both NumPy and CuPy. It contains just 19 lines of code except comment and blank lines, and several times faster with CuPy, and n of 5 million and k of 2. Here, when observation x as array is supplied as NumPy's and the array, this code runs with NumPy, and when observation x is supplied as CuPy's and the array, this code runs with CuPy. You can get a module NumPy or CuPy module object with this CuPy.getArray module function, and we conventionally assign the returned module into xp variable and use this xp variable as module in the following computing. Then I shortly introduce CuPy's advanced features. CuPy provides fascinating features beyond NumPy for performance. For example, element-wise kernel and reduction kernel for making your custom kernel function. And CuPy also provides the raw kernel facility. With it make you easily use raw CUDA-C kernel function from Python. And the fusing feature combines multiple kernel invocations into one call for spatial and temporal efficiency. And CuPy has a memory pool feature. CuPy manages and reuses GPU memory with its own memory pool, and it is triggered by Python's reference counting. Lastly, any feedbacks are welcome. CuPy is an open source software, and your contributions will be highly appreciated. And what we'd like to know, what do you use CuPy for? How do you use CuPy? What features of CuPy do you want? What part of CuPy do you want us to improve? And please contact us at Slack channel, shop general CuPy, and GitHub issues. Thanks for your interest in CuPy, and personally CuPy today, and your contributions are always welcome. You can install CuPy with pip install CuPy-CUDA 101. And I list CuPy's some resources, official website, GitHub, sample codes, forum, and Slack channel. That's all. Thank you very much.
Thank you very much, Masayuki. Does anyone have any questions? Yes, the question here at the front. I think it's better if you use because I can't hear you in the translator.
Yeah. Are you planning to extend CuPy for using TPUs as well?
TPU, Google's TPU?
Tensor
processing unit?
Yeah.
Currently, we have not such plan to make CuPy runs on TPU. Yeah.
So I have a question. Chrisman mentioned that there is some work in running CuPy on OpenCL, but running CuPy on OpenCL instead of CUDA. Is that a thing?
Instead of OpenCL instead of CUDA?
Yeah.
There are some efforts to make CuPy runs on OpenCL, but it is not our It does not have high priority for us, so the priority is not so high, rather less. Yeah.
Okay. And small follow-up question. So if I was going to try CuPy in one of my projects and I wanted to use continuous integration,
yeah.
How do you guys run that so that there's a GPU that you can test?
Sorry, one more, please.
The continuous integration services like Travis and Circle.
Travis, yeah.
Do they provide GPU, or do you guys have something in-house, or how does that work?
We use the in-house or our own CI platform, and
I see.
Yeah, because usually CI platform does not support GPU.
Exactly.
Yeah.
So and I guess your platform is not open for anyone to just use, right?
Currently private for ours. Yeah.
Okay.